Okay, I guess we should get started. Turn one light off. Middle it. What do you think?
That's a good comment.
I'm going to steal some new colors from some new markers from somewhere. Yep, some previous lecturer, hopefully it wasn't me, walked off with the chalk.
Oh, all of them. Do you need? I can run downstairs. Do you need?
Yeah, actually, that would be great.
Yeah.
Thanks. I don't think I need too much chalk. I really need enough chalk markers today.
Yep.
Okay, we're going, guys. Right. So today's class is on again one of these background foundational topics, tensors and exterior calculus. So really, we're going to spend a lot of time talking about some really basic concepts of differential geometry. Amazingly enough, linear algebra is top of the list. So yes, linear algebra is a useful subject, an extremely useful subject in many fields, including differential geometry. We've seen it already. You know, the tangent plane of a surface is defined via linear algebra. But in any case, linear and so-called multilinear algebra is also very important for us in differential geometry. So I'll go over some of the key ideas in multilinear algebra. And that'll bring us to the definition of a tensor bundle. So we'll talk about tensors and bundles and so on. And well, I won't spend too much time there because it's maybe sort of too abstract. We don't need all that. So I'll talk about two examples that we've seen. Well, one that we've seen before, symmetric tensors, and one that we will see in more detail in upcoming lectures, alternating tensors. And then we'll go into some ideas behind exterior calculus and Stokes' theorem and Hodge theorem and all that. So the lecture today is kind of a fly-through. It's like we're in an airplane, we're coming down a little lower than 330,000 feet. We're flying over the ground, we're going to fly back. We won't do too much heavy math, I hope. But on the other hand, lots of definitions and some hairy slides thrown in. Okay, so we're going to talk about linear algebra on a vector space when you have an inner product defined in this vector space. Okay, so an inner product on an abstract. So think abstract vector space. Of course, the vector space we're going to talk about is, of course, going to be the tangent plane of the surface. But let's keep this as abstract as we can for a little while. So V is any vector space. I suppose it has n dimensions. And an inner product in V is a bilinear, symmetric, and positive definite function, which is denoted by these square brackets with two slots. The little dots are two slots where vectors go. So this is the inner product of the two vectors, V and W. And when we say bilinear, symmetric, positive, definite, well, bilinear, number one, means V plus AW X is equal to inner product of V with X plus A times W with X, and also V, comma, W plus AX is equal to V inner product W plus A times V inner product X. So bilinear means linear in each slot separately. Right? So bilinear means linear in each slot separately. And then symmetric just means that inner product VW equals inner product WV. And positive definite means that this inner product, VV with itself, is bigger than or equal to 0 always. But it can be equal to 0, and that should be if and only if V itself equals to the 0 vector. So these are the three conditions which defines an inner product. Symmetric, bilinear, positive definite function of two vectors, of V on V cross V. And this is the obvious question. Okay, the inner product. So once you have an abstract vector space with an inner product, then all the usual constructions that you're all familiar with follow. So in particular, you define the norm, you define the notion of orthogonality, and then the notion of orthogonality extends a bit to subspaces. So if there's a subspace S, then you can define its, I guess I didn't write this here, but you can define this decomposition into parallel part and perpendicular part, and you can also have the orthogonal complement subspace as well, so the set of all vectors orthogonal to S. And you can have orthogonal projections. So this whole theory carries forward in a very abstract setting, and all we need for it is notion of inner product, which is these 4 lines of definition right here. Okay, thanks for that, Marcus. Okay, so vector spaces with an inner product on. Okay, so that's just frame the topic. Now the first new concept, of course it isn't that new because you've probably seen it in all various guises before, but the first new concept, let's say, is the idea of a dual vector, or the dual space of a vector space. So this is a simple definition. So the dual space consists of all linear functions on the vector space itself. So, I don't miss anymore. So any function, I've used the Greek letter xi for this. So any function xi which is linear on the vector space. So by linear, I just mean, xi of x plus aw is equal to xi of x plus a times xi of w. Of course, a is the scalar, these are real vector spaces, and vw belong to the vector space. Okay, so the dual space is just a simple object. It's the space of linear functionals, or we say linear functionals. The space of linear mappings from V into R, otherwise linear functionals, on V. And V star is a vector space. So this is it's a key sort of next step in the abstract chain of ideas. You get a new vector space over the vector space V. So it's a new vector space, simply, so V star, a vector space, simply because if I take 2 functions, if I take xi and zeta, terrible notation, but I'm going to use it anyway, in V star, then quite simply, xi plus zeta and a times xi are both linear functions. Adding numbers together, adding the functions together gives you a new linear function. So for very simple reasons, V star is a vector space. But the slightly deeper thing is that the dimension of V star is the same as the dimension of V. So the way you see that is you just construct a basis. Right? If you want to know what is the dimension of something, you need to construct a basis. The definition of dimension is how many elements are there in the basis. So since V star is built from V, it stands to reason that we're going to build the basis of V star from the basis of V. So sure enough, let's take a basis for V, just any set of linear independent vectors will do, and let's define the so-called dual basis. This is a set of linear operators, linear functionals, linear operators, whose value on the basis are defined like this. Omega is the ith one. Omega of I acting on a vector, on a basis vector, is 1 only if we choose, if and only if we choose the ith basis vector, and 0 otherwise. Okay? So why is this thing a basis? Well maybe, okay, well, so why is this good enough somehow? Well, so if xi is a linear functional, so if this thing is in V star, then we can look at the values xi at E1, xi at E2, and so on. Let's just call these numbers, let's call them A1, let's call them A2, and let's call this AN. Right? So how do I know, okay, what's the question? The question is, why is that a basis? Well, I've got to answer 2 things, linear independence and spanning. I've got to show that those guys are linearly independent, and I also have to show that those guys span the space, the omegas. Well, let me show that the omegas span the space. And maybe we'll leave linear independence for an exercise. Why do these omegas span the space? Well, to answer that question, I'm going to choose a guy in the space, and I'm going to show that I can write it as a linear combination of the omegas. Right? Okay, how am I going to do that? Well, I need coefficients. Here are my candidate coefficients. I'm going to take xi evaluated on the first basis function, call it A1, and so on, psi the last base function AN. And so the claim is that psi is equal to a linear combination of the AI's omega i's. I goes from 1 to n. And, well, how do you check that? So this is the claim. How do you verify the claim? What do you have to do to verify this claim? Yeah, you want to check it on any vector. So what you might do is you'd say, okay, let vector v be summation v I e I, and now check psi on v, and you get something. Check this guy, I should say, check this guy on the v's, and you get something. And then check this guy on the v's. You're going to get something else, and you want to make sure they're the same. So that's how the proof would go. That's how the proof would go, right? You have this proposal for what psi should be, and you have what psi actually is and how it actually acts on the basis, and you just check that they're the same. Okay? So, right. A similar proof will get you, proof of similar ideas will get you linear independence. So let's leave that as an exercise. In any case, the object to leave this slide with is, okay, we've got this dual space. The space is linear functions, linear operators from V into R on the vector space V. Okay, so far so good? Has the word dual space cropped up in your past?
It did last week, yes.
Well, okay, I mean last week, but I mean like before. In the distant, misty past. Okay. Right, so what happens, right, so we've got this inner product space, and I want to know what extra structure I have floating around when I consider the dual space of an inner product space. So what happens when there's a dual floating around? What happens when there's inner product floating around? Okay, so let's suppose we have this inner product space. So we've got four points here, basically 3 constructions. So we have the sharp, the flat, and the induced inner product. Okay, which one comes first? Actually, flat tends to come first because it's easier to explain. And then, okay, so what's this flat operator? Well, it's written down, but I'll explain it. So if V is in the vector space, and the idea is you automatically get for free, you get a vector of the dual space. You get not a vector, but an element in the dual space, a function of the dual space. You get one for free. And that's because you have an inner product floating around. So you say that for every W in V, you get the action is W maps to inner product of W against V. So therefore what you're getting, so you get this psi, which is like V inner product with V. Where this is your free slot. Right? Okay, so the element of the dual space you get for free is the operation of taking an inner product with V. Right? So the input is any vector, the output is a scalar. Right? So this guy is in V and this guy is in the scalars. Okay, so this is the guy you get for free, so let's give it a special name. You're going to give it the name V flat, where flat is the musical term, which to me looks like a B. To Justin, it looks like something different, but to me it looks like a B. So I'm trying to draw it like a sort of a stylized B. But in any case, that's what it's supposed to look like. Musical notation. Okay, so that's the flat operator. It's the element of V star you get for free because you have an inner product. So given a guy V, you get an element of V star for free. Okay, so the sharp is kind of the inverse operation of this. So given a xi in the dual space, there exists a vector v in the original vector space such that xi of anything equals inner product with that v. Okay? So it's the inverse operation. It says there exists, so given an arbitrary linear functional, there exists a vector such that that arbitrary inner functional is of this kind, inner product against something. So there exists this vector v. So again, you give it a name. Xi flat. So you give it that name. And as I say, they're inverse operations. The sharp and flat is inverse, and flat and sharp are inverses. So they're inverse operations of each other. An important name that I should put on the board for you guys is the Riesz representation theorem. So the existence of this sharp operator is in fact the Riesz representation theorem in finite dimensions. It's sort of trivial to prove, actually, once you work it out in a basis. You actually come up with an explicit formula for xi. And there's a slightly less trivial proof that is actually valid in Hilbert spaces, which are infinite dimensional inner product spaces. But this Riesz representation theorem is valid in all sorts of infinite dimensional spaces and has ramifications for partial differential equations. We won't go there, but just to say that maybe you'll come across the words Riesz representation theorem for a while, and well, you know it has to do with an existence result in an infinite dimensional linear space. And if you want an intuition for it, it's the sharp operator in finite dimensions. Yeah, it's unique. Yeah. Okay, so these are the three. Well, this is sharp and flat, the inverse operations. And then the last thing is, if V itself, if V carries an inner product, then V star inherits, V star, V dual, inherits an inner product. So the inner product is simple. I've written, oh, this is dead. I've written it down on the board here. So the inner product of two linear functionals is, well, first you take their sharp operators, you take the sharps to get vectors, then you take the ordinary inner product of those two vectors. So this is the definition of the inherent or induced inner product in V star. Once you have sharp, you can make these things vectors, and then all of a sudden you can apply the vector inner product. Okay, so that's what happens. That's the extra structure that the dual space has when you carry an inner product around. So far, so good? Yeah, please.
So in the process of going through, the choice of W matters.
The choice of W. Where? Up in here? There's no W. What do you mean by W? You mean?
You have to choose a vector towards a sharp operation.
No, you don't. No, you don't. No. This is an indirect definition of the sharp operation. Right? It says the sharp operation is the unique vector that reproduces the action of xi. Right? So W is your test vector. So xi on W should be the same as whatever this thing is. But this, again, inner product against W. So it's an indirect definition for xi. Yeah, but it turns out that you have to prove this. But it turns out that that definition is enough to uniquely specify xi sharp. And in fact, a better, even sort of more practical answer to your question comes on the next slide. Because once you do a basis, you can get your hands dirty and you can compute everything.
So this can be defined without basis?
Pardon me?
This can be defined without a basis?
I just did.
Okay.
Yep. Yep. All of this is basis-free notation. So it's, so I guess, so actually this is something that Trent brought up as well. Like you do actually have to prove that there's a unique, that this specifies something uniquely. It's good enough just, it's perfectly well to just say that, but in order for that to be something real, you have to define a unique vector. That there exists a unique one. And that is something that you can prove. Okay, so, yeah, so like I said, all of this stuff is abstract. It lives, all these definitions so far make perfect sense without a basis. And sometimes you don't want, often you don't want to work in a basis. Two examples. First is, if your vector space is infinite dimensional or extremely large in the practical sense. If you're simulating a differential equation on a computer, what you're really doing is using a very large vector space. In any case, sometimes you want to treat your vector space as infinite dimensional, so you don't want to choose a basis. You want concepts which exist independent of the basis, and you want ways of manipulating them which is independent of the basis. Second, in differential geometry, in order to prove something is independent of parameters, it also helps when you're dealing with vector objects and tensor objects that your definitions are independent of basis. Okay, so let's suppose we have a basis, and once we have a basis, then you can construct these Gij, these coefficients of the inner product, with respect to that basis. If the basis were orthonormal, then the inner product of EI with EJ would be 0, unless I and j are equal, and then it's 1. But in general, if the EI bases have some arbitrary basis, they're not necessarily going to be orthonormal and be nicely positioned with respect to the inner product, so you just get these coefficients Gij. Okay? And then G upper ij are the components of the inverse of the matrix Gij. So this is what you have to define to work with all this stuff when you work with the basis. So one quick aside here. So this is not a British sitcom from the 80s. This is actual modern day important mathematics. Okay, so so indices. These vectors, a vector v, when you don't talk about a basis, when you just want to represent a vector v as a thing in a vector space, you say v, right? But when a basis is floating around, suddenly it becomes a linear combination of basis elements, and you need indices to encode them. So the way you say this is you say v is equal to summation over I, over the basis 1 to n, of vi e I. So vector components upstairs. Vector indices upstairs. And the vector basis index downstairs. Okay. If you have a xi, this is a function on the vectors. It's a dual vector. So this guy belongs to vector space v. This guy belongs to v star. This xi, it gets written I equals from 1 to n, xi lower I, omega upper I. So again, you have your dual vector indexes downstairs this time. Your dual vector indices go downstairs, and your dual basis indices go upstairs. This is convention. But it is a useful convention to, especially when you're dealing with tensors, which end up being these mixed objects, which sometimes are dual and sometimes are not dual. It's important to keep account of what's dual and what's not. So this is the convention that we use. The dual vector indices go down, the vector indices go up, and it's the opposite convention for the basis. And I should say, why is that G lower ij right there? Well, G lower ij has two lower indices because this is sort of a dual. This is sort of a dual kind of object. G is kind of a dual object. So I should say, I guess I should show it like this. So I should say this inner product is a dual kind of object, right? It's sort of a dual object, except it operates on two vector slots. So because it's a dual kind of object, it has coefficients that are dual indices which are down. The indices of the coefficients are down. Okay, so this is the aside. Just want to describe this upstairs, downstairs convention to you. And G upper ij is defined, is just convention of indices go upstairs. This is, yeah. Okay, right. So, once you have a basis, let's work some stuff out. Okay, so these 4 points here. So, I can, if I know what the basis is, I can give you, if I know what the basis EIs are, you can construct the dual basis from the, from these guys, right? So the dual basis ends up being take the EJs and raise them, take the EJs and multiply by the inverse matrix. Okay, why is that true? Why is point number 1 true? So it's true for this reason. Let's take omega I acting on EJ. Let's look at that. Okay, so let's plug in my proposed formula over there. This is sum over J of G upper ij, EJ sharp. Maybe I should make this an S. EJ sharp acting on ES. This is summation over J. By definition, G upper ij inner product of EJ with ES. Remember that something sharp equals, as a linear form, equals, or as a linear functional, equals take the inner product. So this is, you can see where this is going, right? This is G, this is summation over J, G upper ij, G lower JS. Clever, huh? Inverse matrix, the matrix. So, and this is the matrix multiplication. This is the multiplication of these two matrices, right? Multiplication of G with G inverse. So this equals to delta upper I lower j, which of course means 1 if I equals to j and 0 otherwise. Okay, so that's why that first formula is true. Okay, so we get a bunch. So once you know this, then you can do a bunch of tricks, right? You can calculate all these sharp and flats and inner products, right? So if V is a linear combination of VI, EI, then you can compute V sharp. You can compute V flat. This is going to be a linear combination of lower indices Vi omega I. So I want to say this is different from this. Okay. And I can work out a formula for that V lower I. That V lower I is take the upper J's and sum them against the matrix coefficients. Similarly, if I express xi as a sum of coefficients on the dual basis, then, oops, that should have been a xi here. I guess this all should have been xi's. This xi sharp has coefficients f upper I, where f upper I is equal to g upper ij summed against f lower j. So this is right. So these are the formulas. You can check these by plugging stuff in and following your nose. You'll see that those formulas hold true. Now, because of this fact, right, an upper index goes to a lower index and it gets multiplied by g lower ij and so on. Because of this, the g lower ij and the g upper ij are called raising and lowering operators sometimes. You'll see that a lot in relativity theory, in Einstein's theory of relativity theory textbooks, mathematical physics textbooks. So the matrix of G, the inner product, and its inverse, raise and lower. What this really means is performs the sharp and flat operations. It takes you from vector to its dual and vice versa. Okay, finally, if you have two covectors, two functionals, xi and zeta, then you take their inner product, you can work out that it's this bilinear product of the coefficients, but with the inverse matrix stuck in there. So you just work all these formulas out when you have this non-standard, non-orthogonal linear product floating around. And of course, if you do have an orthonormal basis, then the GIJs are just either 1 to 0, depending on if I is equal to J or not. And the sharp operation is trivial, and the sharp operation is trivial, and the flat operation is trivial. Coefficients don't change. Like if, sorry, you just frowned. So if this matrix is so delta J is the identity matrix, right? So if the identity matrix is the matrix that you're working with, then this, then there's identity matrix right here, right? So this is a trivial sum, hence you get this formula. And similarly, if you put the identity matrix here, you're not taking any linear combination of these p's, so you're getting a trivial formula again, you're getting this formula there. Okay, make sense? Right, so the upshot of this slide is if your matrix of the inner product is something non-trivial, then you have to work out formulas for sharp, flat, and inner product, and well, there they are. Okay, so next slide. All right, getting scarier and scarier. So, tensors. What is a tensor? Okay, so there's a lot more that I can say about tensors than what's on this slide, as you can imagine. But maybe we don't need all of that. We actually need very little about tensors, except maybe to know they exist. Maybe 1 or 2 tensors as we go along, and we'll explain them as they come up. But in any case, here's the general slide on tensors. So let's just look at the first 2 lines of the slide. So you need to be on a vector space, you have a vector space floating around. An inner product is not necessary. And if you have an inner product, then there's extra stuff floating around. But in any case, you start with a vector space, and then the tensors over that vector space, they're sort of derived structures, the tensors over that vector space are multilinear functions on a vector space with vector output, in fact, multi-vector output. So the idea is this space of V star V, K times the dual tensor, K L times the ordinary vector space, the so-called K covariant and L contravariant tensors, is the space of multilinear functions from K times the vector space into L times the vector space. So the input is K vectors, the output is an L-fold, or an L-tuple of vectors, and the function f is multilinear in each one of its slots. So in other words, you have this kind of a formula which holds. You have f of, let's consider, I don't know, the ith slot, v plus aw is equal to f of v plus a times f of w, right? So that's true in all the slots. Every slot has this linear behavior. So an example of a bilinear form is, or bilinear tensor, is the metric itself, because it's linear each of the 2 slots on either side of the comma. Okay, so these are the tensors. So a couple of basic facts. The dimension of this space is large. It's n to the k plus l, where n is the dimension of the vector space V. How you know this? Well, you can write a basis in terms of the e's and the omegas. We'll look at special examples later. The next is if V carries inner product, then all these tensor spaces carry inner product too. And furthermore, they have sharp and flat operators. So, except the sharp has to also choose an index, right? So what does sharp do? It takes something dual and gives you something vector, gives you something vectorial. And then you can have a sharp operator, which operates in the first slot, the second slot, the third slot, all the way up to the k slot. You can have k different sharp operators, which pull down or which dualize any one of those slots. And same for the flat. So you have lots of sharp and flat operators. And then these things called, finally, another thing is, there are these operations called contractions, where you take a v factor and a v star factor and you combine them. I'll show you an example. I don't need to describe it in any more detail here. I'll show you an example later on. But there are these contractions which take KL tensors to K minus 1, L minus 1 tensors. Because you kind of pair up one V with one V star and they annihilate each other. Okay, so this is, let's just say, be aware that there are these tensor objects out there. They're multilinear functions that give multi-vector output. And they do appear all over the place, and you've seen one tensor already, and that is the metric. The metric is a bilinear. It goes from, it's a K0 tensor. The metric is a K0 tensor. It has two vectors as input and scalars as output. So it's a K0 tensor. Okay? All right, so that's maybe all we need to know here. Just know that these things are out there. Now we'll go through two examples. We'll start with the familiar one, then the symmetrical linear tensors, which we just talked about. So a symmetric 2-0 tensor is an element of V dual tensor V dual. So two vectors in, scalars out, which is symmetric. So A of V comma W equals A of W comma V. So an example of this thing is the metric tensor. But we've also actually seen a second example, which is maybe something other than the metric. The second fundamental form at a point. If V, in that case, in my little boxed example there, in this case, V was the inner product, the tangent space of the surface at a point, and A is the second fundamental form at the point. Right, so this is another example, which is not the metric, that we've seen already of a symmetric 2-0 tensor. Okay, so just how do you work with these guys symbolically in connection with what we've seen so far? Well, okay, so how do I represent these guys on a basis? Well, I've got to say, in a basis, I've got a sum over coefficients of my basis elements, and it turns out that my basis elements have this nice symbolic form of the tensor product of the omegas. So what does tensor product of omega mean? Tensor product of omegas means, if I put a vector and another vector here, what does it mean? It means do omega I on the first vector and multiply it by omega j on the second vector. I hope you can tell my W and my omega apart. Maybe make these even rounder. So the tensor product basis is defined as this bilinear product basis, right? So, so when I say this, what I mean is that A acting on vector V and W is equal to summation Aij acting on omega I acting on V times omega j acting on W. And then if you want to work out what V and W are, if you say V is equal to summation Vs Es and W equals summation Wt Et, you stick those guys in there and you're going to get summation Aij omega I acting on Es times V upper S, and then omega j acting on E lower t acting on times Wt. This business here gives you delta Is. This business here gives you delta Jt. And so your end product is very simple and familiar. That's the key. It's this. Okay, maybe put this one in the box. Because this is the familiar formula. So I'll turn around in a second here. This is this. That's the key formula. Okay, what's the purpose of this calculation? It's to somehow convince you that all these tensors and upper indices and lower indices and bases and dual bases really come back to something you've seen before. It's just a formalization of something you've seen before. Right? You have seen this way of writing down a symmetric form, right? Standard, maybe the better way of writing this is the vector V, the vector of coefficients V transpose times the matrix A times the vector W. So I'll take the vector signs off. Square brackets being vector, right? So let's say, yeah, so this is this. Okay, so, right. Okay, so that's the first bullet point. Okay, so the second bullet point. Okay, sorry, any questions on the first bullet point? I still see some hands moving, so I'm just going to stop for a second. Okay, so second bullet point. Way back when, we associated a shape operator with the second fundamental form. So formally speaking, what we were doing there we were taking a sharp. We were taking a sharp on one of the slots. Okay, how does it work? Well, let's define a 1-1 tensor. A 1-1 tensor means takes a vector in and gives a vector out. Okay, what's the definition? It's an indirect definition, defined in terms of a test vector W. Okay, so just like before. So it's S of V is the unique output vector such that inner product of S of V with W equals A on V of W. So this is really a sharp operator. It's taking the sharp of one of the slots of the A. Okay, and now we've got to figure out what it is in the basis. Well, in the basis, you write it as a tensor product of the dual basis with the vector basis. So what this means is a vector goes in, gets operated on, gets swallowed up by this thing, gets operated on by this thing. And what you're left with is a linear combination of SJs, coefficients, and the EJs. And the EJ is a vector. So you get a vector goes in, gets gobbled up by the omega, and what you're left with is a linear combination of E's or a vector. And you can work out what the coefficients are, the S's in terms of the A's. And sure enough, I told you it was a sharp operation. That means there should be a raising of an index going on, and the raising is done by G inverse, by the matrix of inverse coefficients of the metric, and sure enough, there's your formula. So this you have to work through, you have to work this out. I'll probably put this on the homework assignment, just to get practice doing this stuff. So I won't do it now, but in any case, you work through and you find that you have to raise the index with the inverse method. Now, in maybe more familiar terms, as I said on the board down here, A is, if you were to represent A as a matrix, or if you were to represent A as a matrix and V and W as column vectors, then you would represent A as, the operation of A is V transpose AW, and then S would be the matrix of S would be G inverse times A. And remember, we did see that. We saw that the shape operator and the second fundamental form were related by the inverse. At that time I said, forget about this detail, we'll see it later on. Let's just pretend that G is the identity matrix and the basis is orthonormal. And so G doesn't even show up. But if the basis is not orthonormal, then this is the formula that relates the shape operator with the second fundamental form. And it's because you've taken a sharp in there somewhere. Now, what's a contraction? Well, a contraction is summing an upper index over with a lower index. That's a contraction. So here's an upper index, here's a lower index. What I do is I sum this. I make J equals to I and I take the sum. In the world of matrices, that's just a trace. But in the world of tensors, because you have all these different indices, you can do contractions all over the place, it becomes more general than the trace. But in this particular case, it's just the trace of this shape operator, S. And so written back in terms of A, it's summation over ij of g upper ij, a lower ij. And maybe my box should have had another thing down here which reminds us what this was. Right? If A is the second fundamental form, S is the shape operator, then this quantity here is the mean curvature. Okay. All right, moving right along. Next example. Next example, we've also seen this a little bit before, but we certainly didn't call it by this name. So it's the idea of alternating tensors. So we just looked at symmetric tensors. The alternating tensors are the ones which are anti-symmetric in every slot. In every pair of slots, I should say. So the definition is just this. It's, you take any two slots, then sigma of v and w in those slots is equal to minus sigma of w and v in those slots. So that's the definition of an alternating tensor. Now it turns out that if the dimension of the vector space V is 2, then this definition is almost completely trivial. In fact, the only tensors you can have are 2 zero tensors. So this is alt, is my space of alternating tensors. Right? So the only tensors you can have are k equals to 2. Can anybody see that? Does anybody know why it's true? Why can't I have an alternating 3 tensor in a 2-dimensional vector space? Can somebody reason through that? Yeah. Okay, let's work it out a little bit. Suppose sigma is alternating. Sigma is an alternating 3 tensor, and V is R2. 2-dimensional vector space. Yeah?
Our linear independence one of them is the sum of the others.
Yeah, that's right.
So then, what are these other two?
Okay, let's run with that. So let's suppose take sigma of V and W and X. Okay, so by linear, so you have 3 different vectors. You know they're linearly dependent. You know they have to be linearly dependent. Okay, this is without loss of generality, let's assume that X is equal to AV plus BW. Linear independence implies that that has to be true. Okay, let's work it out. So now this is sigma of V, W, and then AV plus BW. And by multilinearity, this is A times sigma of VWV plus B times sigma of VWW. Okay. Now what?
Oh, now it's 0 because if you switch V and V, it would be negative.
That's right. Look here. Sigma of VWV is equal to minus sigma of VWV, where I'm switching. Right? So in other words, 2 times sigma of VWV equals to 0, or simply sigma of VWV is equal to 0, and so this is gone. And by similar arguments, that's gone as well. Okay? So alternating tensors, in 2 dimensions, you can't have more than bilinear tensors that are alternating. What about in n dimensions? What alternating tensors disappear in n dimensions? Yeah, n plus 1 higher. Yeah. Okay, right. So we've only got 3 different kinds of alternating tensors. And, well, 0 tensors are just scalars, so we don't worry about those. 1 tensors, well, I'm not really doing anything that I can alternate with. The 1 tensors are just V star, nothing more. So this we understand, this we understand. And now alt 2, the second, the alternating 2 tensors. the alternating two tensors, well, that's a one-dimensional space. And the reason it's a one-dimensional space is because I can give you a nice basis for it. And I can express anything, any alternating two tensor, in terms of that nice basis. And this nice basis is, well, it gives you the determinant of vector. I mean, it's written under what we're writing. It's written there. It gives you the determinant of two vectors. So remember, the determinant operation is a multilinear operation. In this case, this is a 2 by 2 matrix, so it's bilinear. It's a bilinear operation. It's alternating. That's what the determinant does, right? And okay, well, you can by doing some linear algebra, you can prove that if I take any bilinear alternating form, I can reduce it down to a multiple of the determinant. So therefore, I can use the determinant as my basis element for alternating two tensors. Okay, so this determinant should remind you of volume, and we'll get there in a second. Okay, or area. Okay, anyway, so we have determinants as our prototypical alternating two zero tensors. And now, when you have linear product floating around, you get these constructions. You get extra constructions. And it turns out that the inner product gives you a very special alternating two form, a uniquely defined alternating two form, which has meaning in terms of the metric. Namely, it's the area form. So the area form acting on two vectors is the signed area. So you need to take the cross product and see whether you're going this way or that way. But the signed area of the parallelogram spanned by V and W. So as you know, you can write that in terms of a determinant, right? But this is sort of the special determinant that comes from when you have an inner product floating around. Okay, and finally, we have the so-called Hodge-Star operator. Maybe I don't want to go into too much detail on the Hodge-Star operator. I think it'll be practically, Justin will show you all sorts of calculations involving this, and it'll have, when we're doing deck, and it'll have practical relevance, and you'll see intuition for it. But let me just say, the Hodge-Star operator comes out of this. It comes its special structure that arises when you have a vector space, you're considering the alternating two tensors on it, you have an inner product, and now you have this special operation, which is you want to relate the inner product of alternating two tensors with the area form. So anyway, Justin will talk more about this later. Let me just maybe tell you the formulas. Star of dA is 1, star of 1 is dA, and then, so this is star on two tensors, star on zero tensors. Star on one tensors really amounts to rotating by 90 degrees. So, if I take the star omega of a vector v, I first rotate that vector v by 90 degrees, and then I take omega of it. Justin will give you all the intuition on triangles, with triangles and geometry that you'll need to really interpret this.
Yeah.
Let's say the takeaway is this is special structure that arises in this tensorial context.
We actually get lucky in this class that a lot of these kind of scary infinitesimal things are much easier to understand on a triangle mesh. So I have the much easier lecture on Wednesday to give.
Okay. All right. It gets crazier and crazier. Now we add the word bundle to things. Okay. So what we've been doing up until now is we've been doing linear algebra. Even though it looked pretty complicated, we've been doing linear algebra, which means there's a vector space and we're looking at structure on the vector space. There has been no surface, no curved geometry, nothing. No surface, just one vector space. Okay, well, bundles. So tensor bundles. What this means is you have a surface, and of course the surface carries inner products with it all over the place. Sorry, carries vector spaces with it all over the place, right? Here's a vector space, here's a vector space, here's a vector space, etc. So really, the surface is a vector, carries a vector bundle over it, namely one vector space per point. That's what a bundle is, it's per point. There's more to it than that, but anyway, for us, good enough to say it's a vector space per point. And that vector space can vary. It's like a one parameter family, or actually it's two parameter family, one for dimension on the surface. It's a two-parameter family of varying vector spaces. That's a vector bundle. And a tensor bundle are just all of these constructions we've just seen, except at each point. So you have the vector bundle, the tangent bundle, V sub P, tangent bundle vector at each point. You have the covector bundle, or the cotangent bundle, or the dual vector bundle, which is putting the dual space at every point. And then you have symmetric bilinear tensors. You put a symmetric bilinear form at every point, like the second fundamental form or the metric. You can have 1-1 tensors, like the shape operator at every point. You can have KL tensors. You can put this tensor product at every point. Okay, so the next definition always in this world of bundles is the idea of a section of a bundle. A section of a bundle is you make a choice of vector at every point, or a choice of tensor at every point. So the second fundamental form is actually a section of the 2-0 bundle, because I'm making a specific choice of symmetric bilinear form at every point. What's the name of a zero? What is another word for, question for you guys, what is another word for a section of the 0-1 tensor bundle? It's a word you've heard a gazillion times. 0-1 tensor bundle. I guess it's on the board.
Come on, guys, it's literally in front of you.
But realizing it's going to be a thing, right? What are the 0-1 tensors? They're vectors. A choice of vector at every point is a section of that bundle. What's another word for choice of vector at every point? Vector field. Right? A field of vectors is a choice of vectors at every point. Right? So you make this choice at every point. Vector field. Yeah, okay, so sections of bundles. So, 0, 0 is somehow always the trivial special case. So those are scalars. So what's the choice of a scalar at every point? Well, it's a function, right? So every input point on the surface yields an output scalar. That's nothing other than a function on the surface. So a section of the 0-0 bundle are just functions on the surface. Sections of the 0-1 bundle are vectors at every point. That's called a vector field. A 1-0 section of a 1-0 bundle is the choice of a dual vector at every point, or a linear functional at every point. The standard terminology for that is one form. A one form on S is a dual vector at every point. A 2-0 symmetric section is a symmetric bilinear form at every point. Two examples: the metric, it's a varying symmetric form at every point, and the second fundamental form. And finally, the 2-0 antisymmetric guys. These things are called two forms. And an example of a two form is the Riemannian area form. The area form. Remember the thing that you integrate against to get the surface area. That's the choice of determinant of the metric tensor at every point, and that varies from point to point. So it's a section of this 2-0 bundle, antisymmetric 2-0 bundle. Okay, so sections of bundles. We don't need to say, well, okay, I'm going to say a little bit more. But again, high level generality. We don't need all these details. But I'd like you to know what they are because they're sort of a crucial part of differential geometry. Okay, covariant differentiation in a tensor bundle. Yes, it's possible. Because the formulas get worse and worse, right? Okay, yeah, right. Okay, so maybe the first line is all, okay, the first line and something about this formula are the important things on this slide. So the first line is just, you have covariant derivative on vector fields. All these tensor bundles are built up over vector fields. And you have duality, and you have sharps and flats and so on, and you have inner products. Everything extends forward to those higher order tensor bundles. In particular, covariant derivative extends to tensor bundles. And there's a formula for it. There's a basis independent formula for it. There's different ways of describing it and so on. But, right, so maybe something in the middle here. What's important though at the middle? Well, here's my random arbitrary tensor. Let me just throw something out there, something for a big tensor. What you have to think of is the covariant derivative is also a tensor. But it's a tensor which takes one extra vector ingredient. You know a tensor takes vectors in and gives vectors out, right? K vectors go in, L vectors go out in a tensor. Well, the covariant derivative takes K plus 1 vectors in and gives you, again, L vectors out. That plus first vector is the direction in which you're differentiating. So like, the way you would look at this formula is you would say, covariant derivative of sigma acting on a whole bunch of vectors, you know, V1 all the way up to Vn, or sorry, all the way up to Vk, and then Vk plus 1. Well, that's going to be the derivative in the Vk plus 1 direction of sigma on all these other components. So the covariant derivative produces a tensor that accepts one extra input, and that's the direction in which you're differentiating as an input. Right, yeah, so last part of the slide here. So what's important about this, remember the Christoffel symbols, right? So if you choose a basis, you can express everything you need to know about the covariant derivative in terms of the Christoffel symbols, the gammas, these are the gammas, okay? And it turns out that if you work out in careful detail what the coefficients of the covariant derivative tensor are, it's ordinary derivatives, and then all these Christoffel symbol correction factors. Don't memorize them. Just remember that a covariant derivative is an ordinary derivative with a correction factor. And that correction factor is built from the metric, and it has to do with the fact that the metric is changing from point to point. Okay? So a covariant derivative of a tensor is the same thing. Ordinary derivative, and then a whole bunch of correction factors. I don't know, if you stare closely at this, you'll see a pattern, but don't worry about that. If you need covariant derivative tensors, we'll go into detail then. Okay, covariant differentiation happens in a tensor bundle also. That's just the sort of bottom line from that slide there. Okay, so I'm running tight here, so I'm just going to keep moving. Maybe we'll defer questions at this point to the end. Okay. Okay, 3 more slides. Amazing enough. Okay, exterior differentiation. So exterior derivatives, this is something a little bit different from covariant derivatives. In fact, you can define exterior derivatives without a metric. So yes, it's true there are basis independent definitions out there. But anyway, let's assume we have a basis. Okay, so how does exterior derivative work? Well, remember that v, the vector v is a vector. It tells you how to differentiate a function in a given direction. So you don't actually need to use a metric to decide what direction. I mean, v has a direction in it, and you differentiate in that direction. That's defined independent vector. It's something we defined on the very first day. So there's no intrinsic geometry there. So df is somehow is the one form, the 1-0 tensor that you get, which says it's the directional, it's the number which gives you the directional derivative of f in the direction of whatever vector input you take. So it's sort of a formalized version of the directional derivative. I'm formalizing it now as a tensor. We used to just talk about it as directional derivative, but really it's a tensor. It's because it takes as input a vector. It has a vector input. So it takes the input as vector, and the output is the derivative of f in the direction of v. So it's formally speaking a tensor. And you can express it in terms of derivatives of f over a basis. No metric is involved in that definition. But if you did want to bring back the metric, well, the reminder is that df sharp, if you were to dualize with the metric, you get the gradient. So here's a connection between something we define via a metric and something which doesn't need a metric. Okay, so this d operator, it's defined very naturally like this as a directional derivative on alternating on 0 tensors, on functions. But it turns out it has a very natural extension to alternating tensors of any level. And since we're only looking at alternating tensors of dimension 1 and 2, all I need to do is give you 2 formulas. So on a 1 tensor, d of omega is an anti-symmetrized derivative. It's the anti-symmetric part of the derivative. And d of omega on what omega is a 2 tensor is defined to be 0. And some basic facts here is that, which is the way I've defined it, is d of omega equals to 0, so d squared. D operating twice equals 0. And d omega is an anti-symmetric version of the covariant derivative. And as such, I should have put this here, as such, it does not involve the Christophel-symbols. So this is somehow metric independent. This is like the metric independent part of the covariant derivative. It doesn't require any correction factors to make honest to goodness and geometric. This is extremely sketchy and brief because we're doing things only in 2 dimensions. We're only going to use a very limited part of exterior differentiation. But let's just say that we can make a much bigger definition in all the alternating tensors. Just we'll talk about this part of the story on Wednesday in more detail with triangles and good old-fashioned geometric intuition. So you'll see more. In any case, exterior differentiation is out there, the anti-symmetrized covariant derivative, and it's metric independent. And why is it? I'll go back to the slide. And why is that important? Well, exterior derivatives allow you to generalize the fundamental theorem of calculus. So I don't know how many of you have seen this famous formula. This is like, it's got to be the prettiest, well, some people say, the prettiest formula in mathematics. Very simple. It says that if you if you integrate the d of a form over a surface, then that's equal to the integral of the form over the boundary of the surface. So Stokes' theorem, again, is going to come up in all the examples, correct examples, of 1 dimensions and 2 dimensions and 0 dimensions on Wednesday. But differential forms, the exterior differentiation allow you to generalize Stokes' theorem to this here. Let me come back to this in a second. Move back one slide. Okay, exterior differentiation lives in vector bundles, with or without a metric. But if you add a metric, then you get extra structure. In particular, you have sharps and flats, and you have the star operator, and you have duality. You have L2 adjoints. So we define the star operator as the operator. This is an indirect definition. It's the operator delta, which satisfies this formula here. So it's just like the adjoint or the transpose. I guess delta is the transpose with respect to this inner product caused by integration of d. Okay? There's a formula for it. Delta is minus star d star, where star was that Hodge star I talked about a couple slides ago. And some basic concept which arise here, how to connect sharps, deltas, flats, stars to things you've seen before. Well, df sharp is a gradient, as I mentioned. This delta operator is really a divergence. It's a way of expressing the divergence. Divergence, of course, acts on vectors. So if I'm going to make x, if I'm going to use delta, then I better make a form out of it, or I better dualize. So divergence of x is delta on the flat of x. And d has a meaning as well. D itself is related to the curl of the vector field, curl on the surface. And finally, I need to tell you what these things do on 2 forms. So here's your favorite, here's sort of the average 2 form. It's f times dA, and delta of f times dA is really the gradient of f, except rotated by 2, rotated by pi over 2. Okay, so anyway, so I guess we'll see these in action on Wednesday. I'm just, in this brief overview, trying to tell you that these concepts exist and derive from linear algebraic structures on the surface. Okay, right, so now we come back to the slide. Stokes' theorem is this general theorem out there, but what we can do is write omega for, anyway, by special choice of omega and c and so on, we can reproduce all of our favorite theorems from vector calculus. In particular, one of them is the divergence theorem. The divergence theorem is that the integral over a surface of the divergence of a vector field is the integral of this quantity here, which I'll explain in a second, over the boundary of the surface. So if this is my average surface, then here's the boundary, right? Here's the boundary. And the boundary has a vector field, a canonically defined or geometrically defined vector field, which is the vector field that is tangent to the surface, but perpendicular to the boundary. That's my n sub boundary of S. So the divergence theorem says this. You know the divergence theorem from Math 52 or other courses, or maybe course of physics, but it comes back to Stokes' theorem together with these correct use of sharps and flats. Okay, what's left here? Final slide. Okay, the final slide is the so-called Hodge theorem. We're talking about the Hodge theorem. This is relevant in electromagnetism, where the electric field is a vector field, the magnetic field is a vector field. It's also relevant in fluid flow, where the velocity vector field of the fluid is a vector field. And you have these decompositions of vector fields into gradients, and well, this is either a curled part, or you can view it as a divergence-free vector field. You have a decomposition of a vector field into pieces, into a gradient piece and a curl piece. And well, there's always a leftover, well, not always, but there's sometimes a leftover piece called the harmonic piece. Well, what this comes from is a splitting theorem for alternating tensors, a decomposition theorem for alternating tensors. You can prove that the space of one tensors is the d of the zero tensors plus the delta of the two tensors plus the leftover piece, where the leftover piece satisfies these equations, both delta of h equals 0 and d of h equals to 0. And as I said, sometimes these things are, you sometimes have the leftover piece, sometimes you don't. What matters there is the topology of the manifold. It turns out that these harmonic forms, these harmonic one forms, have a topological meaning to them. They only exist when the Euler characteristic of the surface is non-zero. Otherwise, the dimension of that space is 0. So let me give you an example just on a torus. Right? The torus is our favorite manifold with non-zero Euler characteristic. This is not the right number. This should have been the genus of the surface. So a genus 1 surface is a torus, and a torus is this. And well, somehow the harmonic vector fields are associated with vector fields that rotate around the handle this way, and also that rotate around the handle this way. So those are the harmonic vector fields, the rotation this way and the rotation this way. These are obviously related to the fact that the torus has the hole, genus 1 hole. Okay, this is very sketchy, but the reason it's so sketchy is because the proofs take like 2 weeks. We've just covered 2 weeks of material in a day. The purpose of today was to introduce tensors, to tell you about sharps and flats and duality and so on. Maybe we've used G inverse so many times without explanation. Maybe today's class is to explain why G inverse shows up so many times. And just to give you some awareness of all these tensor structures. Anyway, we'll talk more about this. We'll have a concrete example which is implementable on Wednesday. All right, thank you.